Okay, just reviewing the chain rule for function of, for a composite of functions of a single variable x before we start talking about chain rules for functions of two or more variables, okay? It says that the rate of change of f of g of x with respect to x is the rate of change of f due to whatever change there is in g multiplied by the rate of change of g due to the change in x. Now that's a little impenetrable. The idea is that you got an f of g of x. If x changes by a little bit, that changes the value of g. And that change in the value of g causes f to change. And you multiply the rate at which x changes g by the rate at which g changes f. Okay? And we draw a picture of that. Here's our g function, here's our x. We have an x naught and a delta x. So, x starts at value x naught and changes by delta x. Now that causes g to change, because here's our graph of g. If we change x from here to here, then g changes from this value to this value. So here's our change in g. Now, what is the change in g? The change in g is the slope of this graph times delta x. Now, obviously, the slope is changing, so we're saying it's kind of an average slope times delta x. We're going to assume we got a very tiny delta x, so the rate of change of g doesn't change significantly. The rate of change of g with respect to x remains relatively constant. So if we multiply that rate of change, the slope times delta x, we get the delta g. And the slope is what? The slope is just the derivative of the g function at some point in here, and we might as well say it's at the point x naught. So the change in g is g prime of x naught times delta x. And that's our delta g. Now, what does that do to our f function? Well, x has value x naught, so that our g of x has value g of x naught. So on our graph of f versus x, we have our g of x naught. That would be the coordinate of this point on the x-axis. Okay? And we have a delta g that was caused by the change in x here. Okay? So this change in x, at x equals x naught, we get f evaluated at g of x naught, and we get a change in the value of x for their f of x function of delta g. So that our delta f up here is just the slope of this graph times our delta g. What's the slope of this graph? The slope of this graph is the derivative at this point. What's the coordinate of this point? It's g of x naught. So the slope is f prime of g of x naught, and that's multiplied by the delta g to get the change in f. Okay? So, our change in f is f prime of g of x naught multiplied by delta g, but of course delta g is just g prime of x naught multiplied by delta x. So that our delta f divided by delta x, which is our approximate rate of change of f with respect to x, is g prime of x naught times f prime of g of x naught. And that's basically our chain rule, isn't it? Take the limit as delta x goes to 0, you get df dx equals g prime of x naught times f prime of g of x naught. Then you can, kind of eliminate the subscript 0 on the x, and you have the general form of the chain rule, because what we did here applies to any value of x within the domain of g, such that the value of g is in the domain of f, and you got to worry about that too, so kind of think about what I just said. So I say in the limit you got df dx is g prime of x times f prime of g of x, and this says the slope of your g function times the slope of your f function evaluated at g of x. Now that's a really good insight, but it's not an easy one. So don't beat your head against the wall for months trying to understand it. Try to spend a reasonable time getting this idea. Because if you have this idea, then it's easier to understand why you get these various chain rules for functions of more than two variables, or more than one variable.